Welcome to this first lecture in EE404. My name is Umut Orguner, and here is my contact info. You will be able to see it also in the syllabus. First of all, I would like to apologize for the presentation quality here. So the projector here, I'm in a meeting room in Electrical and Electronics Engineering department, and the projector here is kind of circling the drain. So this is going to be slanted just a little bit. I hope you can tolerate this. So this course is about nonlinear control systems. And in this introductory lecture, I would like to talk about what are nonlinear systems and how they are different from linear systems. Also, I would like to talk about the course content here. So my name is Umut Orguner, and I'm in E building if you would like to visit me in the pandemic conditions. And this is my phone number, and the best way to reach me is via email. I generally try to answer quite quickly, but sometimes due to busyness, sometimes I might skip. So if you send me an email and if you don't get a response, please try again. So I would like to talk about this in this introductory lecture about the nonlinear systems, and in general I'm going to be writing on the board here in the same meeting room, and I will be recording the videos, and then we'll be uploading them into YouTube, and then we'll give you some links. So let us start with so this is the only slides that I'm going to use in this course, otherwise I'm going to use the board. So I will talk about first the aim of the course and the plan of the course, and then I will talk about why linear systems are not enough for us. And there is a very, very nice reason actually. And then I will talk about the differences between nonlinear and linear systems. And then I will talk about who should take EE404. So let us first start where nonlinearity is. Nonlinearity is actually everywhere. So the first thing that I tell students taking this course is that there are no linear systems in the nature. You might object me by telling me the circuit components that you have seen in the laboratory. For example, a resistor. A simple, tiny resistor. Even that is not actually linear. Why is that? So suppose that I have a laboratory resistor, and I apply first suppose that it is 1 ohm, and then suppose that I apply 1 volt to it. Okay? Then you would get, because of the Ohm's law, you're going to get just 1 amperes of current. And suppose that now I increase the voltage to 10 volts, and then you would see a scaling property. So I increase the voltage, the input of the system, and then the current that I get, which is the output of the system, increases 10 times. So you're going to get 10 amperes in that case. But what happens if I would like to increase that voltage 100 times or 1,000 times? Suppose that I want to apply the same resistor 1 kilovolt. Okay? In that case, do you think you are going to be able to get 1 kiloampere from that resistor? So probably not, because that resistor is designed to remain linear only in a small voltage operating region. Okay, so if you go outside that operating region, it's going to burn. All right. So if you try to apply just 1 kilovolts to a small resistor, you won't be able to get 1 kiloampere from it, and it's just going to burn, and then you're not going to get any output from it. All right. So linearity is an idealization, and there are always, for any system, there are always limits to this linear behavior, to this ideal behavior. This ideal behavior is only observed in a small region for any system, any natural system, and you will lose that ideal behavior when you get outside that operating region. So linearity is an idealization. It is not a natural phenomenon, actually, and you lose it quite easily by going outside the operating region of your components. So nonlinearity is the main thing that we observe in nature, not linearity. Linearity is only constrained in a small region. So there are no linear systems in the nature. All systems are nonlinear, and that is why studying nonlinear systems is important for a person working on control theory. So when you try to apply your linear control tools, you have to be aware of this fact. If your system gets outside the region of linearity, then you are no longer controlling a linear system and you're controlling a nonlinear system. And you have to be aware of the effects of nonlinearity, what it can cause, what would be the consequences, and what are the solutions that are developed to fight nonlinearity. So the first tool that we use in control to beat nonlinearity is to use linearization. So if you have a nonlinear system, suppose that you constrain yourselves in a small region, small operating region, and suppose you would like to apply control, PID control on that linear system, then we know that the nonlinear systems really would not behave well under Laplace transformation. So in order to be able to get some transfer functions, what you need to have is a linear system. But when you have an actually nonlinear system in your hand, then what you have to do first is to apply a form of linearization to that system, to apply our easy control tools like PID controller. So linearization is going to be an important component of this course. We are going to see the uses of linearization, but linearization is going to be also a limited tool. I will talk about this in this lecture as well. So it is limited, and sometimes it might be not applicable, or sometimes it might fail in many cases. So this course, EE404, is going to be what we can do with and without linearization. All right? And the aim is to provide an introduction to the basic principles, tools for analysis, stability, and control of nonlinear systems. So this is my course conduct for this semester, and that is the main textbook that I'm going to try to follow. Nonlinear control is a very, very advanced topic, actually. So in this department, there is also a graduate course which is much more advanced than EE404. In the undergraduate courses, we try to keep the level of mathematics quite low level. Even that may be advanced for some students, but we try to keep it under control. So in the graduate level, the mathematics is much more difficult, and it would be really a challenging topic in the graduate level. So there are many nonlinear control books, and most of them are actually not readable for an undergraduate student. This is one of the readable books, and you might enjoy really reading the chapters of this book about the topics that we are going to cover. So that is the grading policy that I will try to apply. So 2 quizzes, so there are going to be 5 points each, and 1 midterm exam, 40%, around the middle of the semester, and 1 final exam at the end of the semester. So I will try to supply you with problem sets and some past exam questions. Some of the past exam questions will have solutions, and problem sets will have solutions. And I will provide them for your self-study before the exams. I will actually conduct this course in ODTÜ class. So you would have to be registered to ODTÜ class in order to be able to benefit from the material here. So this is a tentative outline. The course is more or less composed of three main parts. We are here now, Introduction to Nonlinear Systems, but three main parts are analysis, stability, and control. In the analysis part, we are going to be given some nonlinear systems, and then we're going to try to analyze their properties, how they behave. And in this part, we will see many properties of nonlinear systems, and we will try to obtain the tools that we can use to analyze nonlinear systems. The second part is about stability. Almost any course in control systems should contain a part of the topic stability. And analyzing nonlinear stability is much more difficult than analyzing linear system stability. In linear system stability, we just look at the poles, whether they are in the left half plane or they are in the right half plane or on the imaginary axis. Since nonlinear for nonlinear systems, Laplace transform is useless, then we won't have a concept of a pole or zero for nonlinear systems. As a result, investigating the stability of nonlinear control systems or nonlinear systems in general is much more difficult than investigating stability for linear systems. The last part is going to be the control of nonlinear systems, and in that part there are two methods. So last time or so far when I try to teach this course, I could come only until this point. So I always covered feedback linearization, but there was no time for sliding mode control. We will see if the time permits. So the last time that I gave this course, COVID-19 actually hit the world, and after in the second half of the course was just given online again. So I already have some lectures for the second half of this course from this point on. So now I'm going to cover the first half using the videos, and then I will give the second half using the videos for the last year. And the last year's videos were unfortunately a little bit more primitive. We didn't have this board option last year, so I just prepared some lecture notes, and I actually spoke in a video to tell the students those notes. So the second half format is going to be different than the first half's format. All right. So this was, and here there are the chapter or section numbers that are in the book that would cover the related topics. So now let us look at why linear systems are not sufficient. So in this, most of the control theory is related to the linear systems. For example, PID controller is a linear controller, and we design PID controllers usually for linear systems as well. A linear system in state space form would be looking like this: x dot is equal to ax plus bu. All right, it would look like this. And on the other hand, as I told you, there are no linear systems in the nature. Therefore, the nature looks like this: x dot is equal to f of xu. I might guess that you might be in this video, you might be having some difficulty seeing the board. It is because of this bright slides here. When I turn the projector off, in the actual lectures, you will be able to see the board much more clearly. Okay, so don't worry about it. In this lecture, it's not really critical, too critical that you see the board. So try to manage just for this lecture. So this is what we know how to control. We know everything about linear systems, but we don't know since the reality is not represented by a linear system, we usually don't know how to control this system. So the first thing that we try to do is actually to try to convert such a system into such a linear system. Okay, so almost all of our control tools are developed for linear systems, so we have a toolbox that is useful only for linear systems. And since the reality is like this, the first thing that we try to do is to try to use our already developed toolbox. And how do we do it? We try to convert this nonlinear system into a linear one first. That is the first thing that we try. Okay? And that is called linearization of a system. Suppose that this function f, this nonlinear function f, looks like this: a nonlinear function of x plus a linear function of the input. Of course, it can be both a nonlinear function of state and the input, but we will see that case later. In this presentation, we have just a very simple linearity for the input and a simple nonlinearity for the state here. So this function is still a nonlinear function because of this f of x. So the first thing that we try to do, suppose that this f of x would be looking like this. This x is a scalar, and f of x would be looking like this. It's a nonlinear function. It doesn't look like a line anymore. All right? So the first thing that we apply to control such a system is that we apply linearization. So we choose an operating point. This operating point was chosen as 0 here, the origin, and then we try to approximate that nonlinear function in an operating region just with a line. Okay? We represent the nonlinearity around an operating point just using a line segment. We are going to see the tool that we are going to use for this. It's just called a Taylor series expansion of this function f of x around operating point 0 here. And then what we do is that we replace this nonlinearity with this approximating line. Okay, then it's going to give us a linear system that we can use to apply our linear control tools. But as soon as you look at this picture here, so this function f and the approximating line here, approximating linear function, as soon as you look at this picture is that you can see the limitations of linearization. If our control system, if the system that we would like to control remains in this small operating region, then the approximation of f with this line is quite accurate in that operating region. Okay? But if my system has a larger operating region, if x can come here or it can go towards there, then you see that this simple line really cannot represent this nonlinearity anymore when we are far away from the actual operating point that we applied linearization for. Okay? So linearization is a limited tool if you want your system to have a very large operating region. Linearization is only valid in a small operating region, and if you go outside it, you're going to get very wrong results from it. In that case, this linear system would not be able to approximate this actual nonlinear system anymore, and your controller would be a faulty controller because it is based on this wrong linear system. Then you're going to lose your performance, and even sometimes you might get unstable closed loop systems at the end. So then what can we do? So the solution that is proposed for such cases, so if you would like to run your system, control system in in a very large operating region is to apply multiple linearizations at the same time. At this operating point, we obtain this nonlinear system. At this operating point, this linear system. At this operating point, we apply another linearization. At this point, we apply another linearization, etc. Okay? So this is what I already talked about. Linearization is very bad when we go away from the operating point. If we are close to the operating point, linearization is fine. It's a good approximation. But if we are away from the actual operating point, too far away from the operating point, then the linearization will be very bad. So in that case, we actually linearize the system at multiple operating points. Okay? So at each operating point, we apply a linearization, and then we switch up. So for each of these lines, we have a different linear system in that case. So each of these lines would give us a different linear system. And for each of those linear systems, we design a controller, and then we switch our controller by looking at the operating point of the actual nonlinear system. If the system is operating close to this operating point, we use the controller designed for the original approximating linear system. On the other hand, if our operating point comes close to here, we would use the controller designed for this line here, for that linear system. All right? So we switch our controller depending on the operating point of our system. And this idea is called gain scheduling. So we schedule our gain means more or less a controller, and we schedule our controller depending on where the current operating point of the system is. So this is one of the basic ideas of nonlinear control, but still this function represented by these lines here, it is still a nonlinear function, and the overall system, your overall system would still be, your controller would still be a nonlinear system, and you would still need some nonlinear system analysis tools in order to investigate the behavior of such systems. So there is no escape from nonlinearity if you want to deal with a nonlinear system in a large operating range. So now let us, so if a nonlinear system is the behavior of a nonlinear system is actually close to the behavior of a linear system, then we might not have a problem actually. But this is usually not the case. Nonlinear systems are really usually not very similar to linear systems in behavior. And they have some distinctive behavior that is not observed in linear systems. So now let us try to look at those behavior here. I'm comparing the nonlinear systems and linear systems, and I would like to tell you about what behavior a nonlinear system can have different than a linear system. So the first thing that you notice when you try to work with a nonlinear system is that the scaling property does not hold. So remember, actually at the beginning of the course we are going to see the definition of linearity. One of the properties of a system that would be satisfied for it to be linear is the scaling property. You probably remember this. When I give the system an input, then you get an output. For a linear system, an input, you get an output. Suppose that I scale that input with the constant 2. I multiply the input with 2. Then what happens in a linear system, if the system has 0 initial conditions, the output is multiplied by 2 as well. Okay? So when I scale the input with a constant, a linear system would give me the scaled output. Of the scaled version of the output that I observe in the first case. All right? Well, but for nonlinear systems, this does not hold anymore. So when you scale the input, the output might be scaled with another constant, or when you scale the input, something even stranger might happen. Okay? So here I'm showing this behavior on a very, very simple system. So this system is a model of an underwater vehicle, and before I work on that model, I would like to give you a similar linear model. So suppose that you have a mass, and suppose that you have some friction, represented by the friction constant B here. This is the mass M. Suppose that mass is 1, and the B is 1, whatever its unit is. And suppose that I apply an input U, which is a force applied onto this system. Okay? Suppose that this is my force F. The input is the force here. So now let me write the mathematical model here. M times, here the output of the system is, let me say it's the position. Okay? So I will actually want the output of the system to be not position at the end, but velocity. But currently, I would like to write the system equations for the position. Okay? So M times x double dot, this should be the net force applied onto the mass. So this is going to be F minus B times x dot. Okay? So this is the linear system, mathematical model, with the mass and the friction. An underwater vehicle system, underwater vehicle would be just a mass and with really a lot of friction underwater. Okay? So here, this is my system from U equals to F to X. Okay? The variable here is X. Now I would like to define the system from F to the signal V, which is x dot. Okay? So I would like to find the system between F and x dot, which is equal to V. So now what I have to do is to just write this equation in terms of V. This equation is nothing but M times x double dot plus Bx dot is equal to F. Now I'm actually, and F is the input applied. Now I'm going to convert this equation in terms of into V. Okay? So V is equal to x dot, and x double dot in that case would be V dot. Okay? Plus B times x dot is V, that is equal to F. So this is my system equation. Okay? The linear system equation when we have linear friction model here. So M and B are 1. As a result, my system would be looking like this. V dot plus V is equal to the input force is U here. Okay? So this is a linear system in this case, all right? Because this is a constant coefficient linear differential equation. Now the system that we are going to see for the underwater vehicle is not a linear system because of this second term. I have here V dot plus absolute value of V times V. Okay? So in this case, this is not linear because of this second term. In the linear system, I had only V here, but in that case, I would have a nonlinear function of V. So here, why that nonlinearity comes here? In underwater or in air, the friction would be usually proportional to the square of the velocity. But here, in the linear system, this is the friction force actually, B times x dot, or it was B times V here. In this friction model that we used in deriving this equation, we took the friction force proportional to the velocity. Okay? That is a linear friction model, and it's a restrictive friction model here. In reality, in a fluid, the friction would be proportional to the square of the velocity. What does it mean? When you actually double your velocity, the friction force that is applied onto you would be quadrupled. Okay, so it is not really very good. And the friction in the fluids is usually called the drag, actually. And in this case, we replace this friction term like this. So we take V dot plus V times V is equal to U. So this is a nonlinearity in this system, and as soon as I include that nonlinearity in my system, the scaling property starts to not hold anymore. All right? So why does it not hold? So suppose that I look at this system. When I take twice the input, when I give the system, when I double the input of the system, V and V dot are also doubled, and for the linear system, the output becomes twice the original output here. So here, I'm giving the system a step input, and I'm looking at the outputs. Okay? So suppose that we look at only the steady state values here. All right? So I will just take this input here, take this linear system here. All right? Suppose that I apply a constant input U equals to 1 for the linear system. Okay? What would be the final value of the output V here? For the linear system, what would be the final value of the output V? V dot plus V is equal to 1. This is the equation that I have, and from this equation I can actually find the final value of the output. I am assuming that the output settles at some point. If the output V settles at some point, I know that after that settling, V dot becomes 0, so then V becomes equal to 1. Okay? For the linear system, if I give the constant input 1, then I get the constant output V equals to 1. What happens when I give the system twice this input? Okay? Suppose that I want to find the final value of the differential equation, V dot plus V equals to 2. I increase the force that I apply onto that system, and what would be the final velocity that I get from the system? In that case, if I set V dot equal to 0, assuming that the velocity settles at some point, I see that V is equal to 2. That is let me write V infinity here, okay? So these are the final values of the velocity. So you see that for the linear system, when I double the input, the output, the final output doubled as well, all right? Now I'm going to do the same thing for the nonlinear system, all right? Let us see what is going to happen in that case. So for the nonlinear system, I have just this system. V dot plus V is equal to 1. I apply the constant input, which is 1 to the nonlinear system, and the output comes to here, somewhere like this. This curve here represents the output of the system. Now, so what is the final value of V infinity in this case? So I know that if the output settles at some point, V dot is going to be equal to 0 at that point. Okay? So then V infinity times V infinity is going to be equal to 1, but this tells me that V infinity should be 1. Okay? Now let us scale the input of this nonlinear system. Suppose that I try to find the final value of the output for this differential equation. I scale the input by 2. I take twice the input in this original input here. So now if the system settles, V dot is equal to 0 and V infinity times V infinity is equal to 2, then what is V infinity? What is the final output? You see that it is going to be just square root 2. All right? So you see that the final output does not go to 2 anymore. Okay? On the other hand, it goes to the value actually square root 2 here. So when I take twice the input, the output now settles at somewhere around square root 2. Okay? So definitely we don't have any scaling for nonlinear systems. Of course, some nonlinear systems might still keep that property, but I'm talking here about the general case. For the general case, for nonlinear system, scaling might not hold, which is a disturbing thing for us. So now let us look at the case of stability. So suppose that I have a linear system looking like this. X dot is equal to AX. Okay? So for such a system, the stability is dependent on the sign of A. Okay? If A is, so I have, let us say, BU here. And what is the transfer function of such a system? Suppose that Y is equal to X. Then if you look at the transfer function of this system, then you would see that it is going to be G of S is equal to B over S minus A. So this system is going to be just a first order linear system. Okay? And its stability is dependent on the pole position. The pole is at A. Okay? So this is the complex plane. If A is in the right half plane or on the imaginary axis, we have unstable linear system. And on the other hand, if A is in the left half plane, then we would have a stable linear system. Okay? So the stability of this linear system is only dependent on this coefficient. And it is independent of the input of the system. Okay? Input can be anything here. The system is either stable or not, depending on A. Okay? So the stability of a linear system is independent of the input that we have. Okay? Stability of a linear system is independent of the input. But for nonlinear systems, unfortunately, the same thing cannot be said. All right? So suppose that I consider the very simple nonlinear system. X dot is equal to U times X. U here is the input, and X is our state, and I consider Y is equal to X here. So you see that in a linear system, can I have such a linear system? This U times X multiplication is a nonlinear effect here. Okay? We see that in a linear system, the input and the state can never be multiplied. Okay? Because multiplication is a nonlinear operation, and it would give us a nonlinear system at the end. So in this simple nonlinear system, we have the multiplication of the input and the state. Okay? And we see here directly that if this U is positive, then this system would be nonlinear, this system would be unstable, X would go to infinity, and if U is negative, then the system would be stable. So depending on the sign of the input, the stability of the nonlinear system can change. On the other hand, for a linear system, whatever the input is, stability is only determined by this coefficient here. Okay? On the other hand, for the nonlinear system, this coefficient can be the input. And in that case, the stability of the system would be dependent on the input. for a nonlinear system. And this is really a very, very basic example of this phenomenon. So it is really disturbing for us. In general, in a linear system, whatever the input is, if I'm working with simple systems, then if I'm working with a stable system, then if I give it a bounded input, then I know that the output always would be bounded. Okay? So independent of the input sign, for example, I can be sure that my output will be bounded if I'm working with a linear system. On the other hand, if I'm working with a nonlinear system, I need to be really, really careful about the inputs that I give to it. Okay? If I give it a wrong input, I might make a stable nonlinear system an unstable nonlinear system, and it would be really catastrophic at the end. Okay? That is a very distinctive property of nonlinear system that is not observed for linear systems. So another distinctive characteristic of a nonlinear system is related to oscillations that we can have. Okay? So suppose that I have a linear oscillatory system. Okay? You might remember this system. So I have just simple harmonic system here. So just some spring effect and just some M here, the mass, and the system is just, and suppose that there is no friction. Okay, so this is the initial point, x equals to 0. That is the equilibrium point of this linear system. All right. Obviously, if the system is at rest, there is no oscillation. Okay. And if I pull this system, if I pull this mass to the point x equals to 1, okay? Maybe I should give you a better drawing here. So let us say that this is x equals to 1, okay? And suppose that I change the initial condition of this system to x equals to 1, I know that because there is no friction, the system is going to oscillate forever between +1 and -1. Okay? So if I give the system initial distance 1 here, this is my x and this is t, I know that the system will oscillate between ±1 forever because there is no friction here. So now, what happens if I scale this initial condition 1? If I scale this initial condition, suppose that I scale it to x equals to 1/2. Okay? So I start this system at this initial condition with 0 velocity. Here I assume initial 0 velocity as well. So suppose that I start my system here. In that case, what would you observe? What would happen to the response? In that case, this oscillatory response is just scaled, because for a linear system with no input, there is no input here, system only works with its initial condition. For a linear system, if I scale its initial condition with 0 input, the output of the system would also scale. There is another scaling property. Okay? So the output is just going to be scaled like this. All right? So it's just going to pass through 1/2 and -1/2 now. Okay? So it's just going to make a smaller oscillation. In the original case, it was a larger oscillation like this. Now it makes a smaller oscillation. So that means that by choosing the initial condition of a system, I can actually change the amplitude of the oscillations in a linear system. I can actually scale the oscillations. So, and that means that I can obtain oscillations with any amplitude for this linear system. This is always true for linear systems. Okay? By scaling their initial conditions, if the you can actually scale the oscillations. You can scale the amplitude of the oscillations. Sometimes for a nonlinear system, this really doesn't happen. Okay? Even if for a nonlinear system, sometimes even when we scale the initial condition, the resulting oscillation amplitude would always be the same at the end. Okay? So we can never, sometimes for some nonlinear systems, we can never scale the amplitude of the oscillations, however much we play with the initial conditions. For any initial condition, sometimes a nonlinear system would always converge to a single amplitude oscillation. Okay? This is an example. Here, different colors would represent different initial conditions, but you see that even though I scale these initial conditions here, at the end the system would always reach the same oscillatory amplitude. Okay? It is this system that is given here. It's a nonlinear oscillatory system, and such a system, whatever you choose as its initial condition, would always converge to an oscillatory behavior with the same amplitude too here. Okay? These type of oscillations, whose amplitude and frequency does not change by changing the initial conditions, are only observed for nonlinear systems. And these type of oscillations have some specific name in the control literature. They are called limit cycles. We are going to spend some time in EE404 about the prediction of the existence or non-existence of limit cycles for nonlinear systems. So sometimes this type of behavior would be good, sometimes it would be really, really bad. Okay? So suppose that you want to avoid these oscillations. In a linear system, you can do it by scaling the initial condition. Just choose a very small initial condition, and then the oscillation will be very, very small. Okay? In the nonlinear system, if you try to do it, in this nonlinear system, you will not be successful at all. Even if you take a smaller initial condition, your oscillations will again grow to the same amplitude. Okay? So if you want to avoid oscillations, working with nonlinear systems is worse. All right? On the other hand, sometimes oscillations are desirable. Sometimes we want oscillations in the system. Okay? What can be the examples? So we really want oscillations in biological systems, for example. Okay? Our heart is just an oscillator. It is a simple biological oscillator, and we want it to oscillate forever. Okay? So we are usually unsuccessful in that, but in that case, oscillations are desirable. Or our lungs, we need to always breathe. We always need to have an oscillation there. Breathing is again an oscillatory biological behavior, and we want that oscillation to continue definitely. So oscillations are sometimes desirable, or if you want to make a signal generator in a laboratory, if you want to create a sine signal somewhere, so that you can work with electronic components, in that case you want that signal generator to oscillate. Or in the clock of a computer, you want that clock to oscillate, okay? So, and you want to adjust its frequency quite easily. And furthermore, you want that oscillation to be robust to external effects, okay? So you really do not want to, or in a radar system, you need to have a clock, because you're just measuring in a radar, you are actually sending an electromagnetic wave and then recording the time instant that it arrives back to your receiver. And you need to know the exact time that it arrives at the receiver, because from that time you are going to get the range of the airplane that electromagnetic wave reflected from. Okay? So you want your clocks, you want your oscillators to be accurate, and you want your oscillators to be robust against external disturbances. And a disturbance for a system might be the initial condition. So a linear system is not really robust to the disturbance of initial conditions, okay? Because if you accidentally give it a wrong initial condition, then that oscillation amplitude would be quite sensitive to the initial condition. On the other hand, a nonlinear system can really be very, very useful in terms of robustness, because whatever you choose the initial condition here, the system would always keep the same oscillation amplitude and frequency for this nonlinear system. So when the oscillations are desirable, therefore, you always want to work with nonlinear systems. You always want this behavior to appear for robustness and insensitivity. So these are the things that I already talked about. You want oscillations in signal generators, oscillators in a radar or a computer, heartbeat, breathing, and these are the cases when limit cycles are desirable or oscillations are desirable, and these are the cases that they might not be desirable. Okay? And when they are not desirable, working with nonlinear systems is really difficult, but when they are desirable, then you need to work with nonlinear systems so that your oscillations have good quality or robustness. So another behavior of a nonlinear system that would be different from the linear systems is their sensitivity to initial conditions. I have already shown you this type of sensitivity. Okay? So here, linear systems, of course, are also sensitive to changes in their initial conditions. Okay? But this sensitivity is not really much for linear systems. So suppose that, I am going to try to explain this just a little bit. So suppose that I choose an initial condition for a linear system, for the simple harmonic oscillator given like this. Suppose that my initial condition is this: x0 equals to 1, like this, and x dot 0 is equal to 0. So initially at rest and with distance 1 from the equilibrium. I have already drawn the response in that case. So this is t, this is x, and the response would be something like this. So it is a constant sinusoid, constant amplitude and frequency sinusoid given like this. Okay? So these points are equal. So now suppose that I perturb, suppose that I disturb this initial condition just a little bit. Suppose that I choose x dot 0 is equal to 0 again. So the initial velocity remains at 0, but the initial position, suppose that I take it to be 1.1. Okay? A very small perturbation means subma, a very small perturbation in the position initial condition. In that case, when I look at the output of the nonlinear linear system for this different initial condition, you would see something like this. Okay? So you would just see an oscillation very close to the original oscillation. Okay? So if this disturbance is small, the difference between the disturbances, the difference between the responses would be small for all time for a linear system. For a linear system, if you infinitesimally perturb the initial conditions, the whole response remains infinitesimally close to the original response. Okay? So here, for linear systems, the behavior is very, very predictable. When I change the initial conditions very little, then the response changes very little from the original response. For nonlinear systems, this is unfortunately not the case, for especially some nonlinear systems. Some nonlinear systems are extremely sensitive to their initial conditions. And This type of behavior, this type of nonlinear systems are called chaotic systems. Okay? So if you have heard about the name chaos theory, this is specifically related to the sensitivity of the nonlinear systems to their initial conditions. Okay? So sensitivity of nonlinear systems to small changes in the initial conditions is called the behavior of chaos. And it is only observed in nonlinear systems. Linear systems are not really sensitive to changes in the initial conditions much. If I change the initial conditions very little in a linear system, the response changes quite slightly and not very much. But for a nonlinear system, this might not happen. So this is a nonlinear system, and its nonlinearity is here. X equals to, I have x to the power 5 here, and that is what is causing the nonlinearity here. Suppose that I consider two initial conditions for the second order nonlinear differential equation. The first initial condition is x0 equals to 2 and x dot 0 is equal to 3. The second initial condition is just slightly perturbed values for both of the initial conditions. Okay? Then I can actually solve this differential equation for these two sets of initial conditions. Okay? And look at the response. So this is what you see for the responses. So the blue curve is the response for the first set of initial conditions, and the red curve is the second response for the second set of initial conditions. Okay? You see that they actually continue to be the same for some time. But when some time passes, they start to differ quite a lot. And at the end, after 30 or 40 seconds, they become completely different. Okay? In a linear system, you never see such a behavior. So this behavior, this closeness would always continue forever. However long time I run the system. It really doesn't matter. But for a nonlinear system, for similar initial conditions, they might remain close, but after some time, everything becomes quite different in the response. Okay? This is called a chaotic behavior, and sometimes this is named as the butterfly effect. So small changes that you make in the initial conditions would cause very large effects in the future. Okay? So the original statement is, does the flap of a butterfly's wings in Brazil set off a tornado in Texas? So a very small disturbance in the wind by the butterfly's wings, can it cause a tornado? And this is really scary because the chaotic systems are not just a mathematical curiosity. They are in nature. And they are actually everywhere. For example, turbulence in fluid mechanics, the turbulence that you observe in the fluid mechanics, or atmospheric dynamics. So the weather is a chaotic system actually. Okay, that is why we cannot predict the weather very well. We can predict 15 days, 3 weeks, but we can never predict the weather the next year. So I can never know how the weather would be next year at this time. That is because the weather dynamics is a chaotic dynamic system, and in order to be able to predict it, I need to know the initial conditions of that system very accurately. If I don't know the initial conditions very accurately, the chaos effect is going to make my predictions infinitely different, extremely different from the actual weather dynamics. Okay? So the chaos theory was actually found by the people working in meteorological systems. So the first chaotic system was found by someone called Lorentz in MIT, and it was a third-dimensional, third-order differential equation which was given like this. And even in this simple system, you would observe chaotic effects. So this system is called a Lorentz attractor, and in its state space, you observe trajectories like this, like a butterfly. It's an ironic It's an ironic thing. So, and when you look at the trajectories of such a system, you can never predict when this system is going to pass from one wing from the other wing into the future. And actually, if you look at the trajectories of the system in 3 dimensions, then you would see that it would never pass a point in 3D space once it crosses it. This is not really very important for EE404, but it's really extremely interesting for me. So the last thing that I'm going to talk about is who should take this course. So EE404 is a nonlinear control course, and it's going to contain really a lot of mathematics. Okay? So if you don't like mathematics, if you are not more physics-oriented person, then you might not really like it. So I'm warning you about this. So my physics is not really that good, so that is why I won't go into physical interpretations quite a lot. I really like working in the mathematical domain. So we are going to be dealing with nonlinear ordinary differential equations most of the time in first-order state space form. And we are going to use some level of linear algebra and calculus. They are going to be useful. And remember that EE404, the feedback control systems or feedback systems course, in the 3rd year is a prerequisite of this course. That is because in this course we are going to use, sometimes, as I told you, we use linear system tools when analyzing nonlinear control systems. And we are going to see that we will be able to use root locus and Nyquist methods in analyzing some specific nonlinear systems. As a result, knowing 302, the topics in 302 might be useful for you. It is going to be useful. And I need to talk here about the mathematics level here. So we are in an engineering department, and I would like to give this course as an engineering course to engineering students. So what I'm going to do is that I'm going to skip most of the proofs underlying the methods of interest. We are going to see some theorems in this course, and I will never be able to prove them. Okay? Because the proof would really require much more mathematics, advanced mathematics, than what we engineers would know. Okay? So I will skip the proofs of the methods. And I will always keep the mathematical rigor in the theorems at a minimum. Okay? So in the conditions of the theorem or in the proofs of the theorem, I will never use really too advanced mathematics for engineering students. So this is because first we are in an engineering department, and second you are undergraduate students. So I really do not want to go into graduate level nonlinear control theory in this course. So I will just try to give you the main ideas of nonlinear control without the most complete mathematical proofs here. So the last year I have given this course, and there were a couple of students who were having double majors in mathematics, and they were not really happy about this. They said at the end of the semester, in the evaluation forms, I never solved them, in the evaluation forms they said that it was a waste of time. So I don't know. This is the policy that I'm going to follow, and therefore in this course it is necessary that you learn mathematics at an advanced engineering level, not less, not more. If you want a nonlinear control course that is proving everything, giving into deep mathematical ideas like they do it in mathematics departments, I'm not going to be able to provide this for you. Okay? So if you are having a double major in mathematics, and if you are expecting me to give a course, a nonlinear control course, like we are in a graduate level or in a mathematics department, you would be disappointed. Unfortunately, this is the case. So if you like mathematics more than at an advanced engineering level, you might not be happy for this course, with this course. Okay. So this was the introductory things that I would like to talk about. In the next lecture, I'm going to be starting on the board with the definitions of nonlinear systems and important concepts about nonlinear systems. First, we are going to learn about linearity actually, because the nonlinearity doesn't mean anything if you don't know what a linear system is. You need to be able to identify a nonlinear system when you see it. So therefore, the first things, one of the things that we're going to see first is going to be the definition of a linear system, and then we're going to learn about types of nonlinear systems, and we're going to base all of the theory that we're going to see on these topics. Thank you very much for watching and tolerating me. Bye-bye.